Welcome back to Real Analysis 1. The point of this video is just to look at the Archimedean Principle, which has two versions. We will state and prove both of them. You can go ahead and read version 1 here. Both of these statements feel so obvious, you might think, like, when would we ever use that? And the answer is all the time. If I had $1 for every time I've said the phrase, by the Archimedean Principle, I would have a lot of dollars. So especially version 2, it seems like such a minor statement, but it's a very useful tool just to be able to use it because we will use it all the time. Version 1, not as much, but let's go through it. What this one says is that for any positive real number x, there is a larger natural number. In other words, wherever x is, the natural numbers continue beyond that. Okay, we are going to prove this statement. What I think is useful to do, because the statement itself is not very surprising, you probably understand right away what it's saying, that natural numbers essentially go off to infinity. Let's go through this symbolically, think rigorously about how to prove it so that we set up and do a rigorous proof. I typically like words more than quantifiers, but here I think it's useful to take this phrase and translate it into quantifiers. So what we are saying is, for all x in the set of real numbers, for all x in the set of real numbers with x greater than 0, there exists an n from the set of natural numbers such that n is greater than x. That x is greater than 0 is one of those foundational hypotheses that we can kind of put above the statement. We are not going to negate this and look at negative numbers. We're always going to assume, whether we work directly or indirectly, that x is positive. So for all positive x in the set of real numbers, there exists a natural number which is bigger than x. This is a statement that's better to do with contradiction. So let's take this if p then q and negate it. So I'll drop a negative sign in front. If it's not the case that for all x this property holds, then there exists an x for which this property doesn't hold. So to negate this, I'm going to say there exists an x in R, which is going to remain positive, such that the property doesn't hold, which means not the rest of the statement. How do we negate there exists an n which is bigger than x? We say for all n is not bigger than x. In other words, n is less than or equal to x. So there exists a positive real number x such that for all n in the set of natural numbers, n is less than or equal to x. Okay. So the negation of our original statement is this. So we are going to set up a proof by contradiction by assuming this to be true. There exists an x which is larger than every natural number, and then we'll show that that can't happen. Going from here to here is always a good exercise. It's always good to practice taking these kinds of clauses and negating them. Okay, let me step aside, erase this, and then we'll come back and knock out this proof. This is going to be a proof by contradiction, so let's let the reader know that. I'm going to use my abbreviation FTSOC, SOC, for the sake of contradiction. So for the sake of contradiction, suppose there exists a positive real number x so that, I'll say satisfying, that x is greater than or equal to n for all n in the natural numbers. If you think back to when we defined the notion that a set is bounded above and perhaps has a set supremum, this establishes that x is an upper bound for the set of natural numbers. It's not immediately obvious, and maybe it's not true, that this particular x is the supremum. At this moment, I know it's an upper bound. But by the supremum property, that's going to tell me that the set of natural numbers does have a supremum. Therefore, thus, x is an upper bound for the set of natural numbers by the supremum property. And I really encourage you to get in the habit of citing every prior result as we move through Real Analysis 1. That's part of the beauty of the subject, is we're just going to build results off of each other. So really try to cite the pre-established axioms in this case later might be pre-established results and theorems that we've shown every time you use one. So by the supremum property, there exists an S in the set of real numbers, which is the supremum, or the least upper bound of n. Since S is the least upper bound for the set of natural numbers, every number which is less than S is not an upper bound for the set of natural numbers. Since S minus 1 is less than S, S minus 1 is not an upper bound of n, the set of natural numbers. If it's not an upper bound for the set of natural numbers, then that must mean that somewhere out there I could find a natural number which is larger than S minus 1. Thus, there exists some, let me use m, from the set of natural numbers so that m is greater than S minus 1. But this implies that m plus 1 is greater than S. I'll say notice m plus 1 is greater than S. Natural numbers are closed under addition, so m plus 1 is also a natural number. But now we're saying that m plus 1 is a natural number strictly greater than an upper bound for the set of natural numbers. That's a contradiction. Since m plus 1 is a natural number, m plus 1 is less than or equal to the sup of natural numbers, which equals S. So I've kind of written contradictory sentences literally right next to each other. So let me just wrap it up, say that we've reached our contradiction. Thus, there is no such X. In other words, there is no upper bound for the set of natural numbers. Thus, for all X in R, there exists a natural number such that n is greater than X, i.e. n, the set of natural numbers rather, is not bounded above. All right, so that is the proof of the first version of the Archimedean principle. This is usually presented as the first version, so this idea that natural numbers just get increasingly large. I am going to state the second version and prove it in just a moment, and that is the version that I feel like we use the most often. So that's the one that feels like a very minor thing, but we are often going to say, by the Archimedean principle, this version 2 result. So here is version 2 of the Archimedean principle, which tells us that if we have any positive real number, we can find a number of the form 1 over n, where n is a natural number, which sits between 0 and y. I've said my interpretation of this sentence, so if you'd like, you could go ahead and pause and read this phrase. It's not too surprising, but it turns out that it's very useful for us to imagine anytime we have a positive number, which could be out here, or more interestingly, it could be perhaps very close to 0. It feels like very close. What version 2 of the Archimedean principle is telling us is no matter how close this positive number y is to 0, we can always squeeze something in here which looks like the reciprocal of a natural number. 1 over, I'll write capital N. Sometimes I do that when I'm trying to grab one particular natural number, 1 over capital N for some natural number n. Okay, so that's really the heart of Archimedean principle version 2. No matter how tiny a positive number is, you can always squeeze the reciprocal of a natural number between that tiny positive number and 0. This is going to be a direct proof because we're going to prove it using version 1. So if you'd like, you could pause and see if you can knock out maybe in 2 or 3 sentences a proof of this, which assumes version 1 that we just proved. All right, direct proof coming up. So to prove the statement directly, we're going to imagine that we have such a number y. Suppose y greater than 0. I'm going to omit writing here that y is a real number. No, you know what? I'll write it. I was going to say we're always working with real numbers. We're not working with complex numbers or anything like that. So often if you just have a real number, you don't really need to state it, but I'll state it here. Suppose y greater than 0 is a real number. Eventually I may omit this because, again, real numbers are the objects that we're working with. All right, then 1 over y is also a real number. That comes from the field axioms. It's the multiplicative inverse of y. It's positive. You can show that. By the AP version 1, what we just proved, by the Archimedean Principle version 1, there exists an n in the set of natural numbers such that 1 over y is less than n. I'm now going to multiply both sides of this inequality by the positive number y, and that's going to preserve the direction of the inequality by the order axioms. I'm not going to write down by the order axioms. I guess field axioms and order axioms, I don't cite them because those properties of how real numbers behave are so familiar to us, but definitely do cite the supremum property when you use it. Okay, thus, 1 is less than ny. And likewise, I'm now going to multiply both sides of this inequality by 1 over n, which exists from the field axioms, and which will preserve the inequality by the order axioms. Again, those like familiar arithmetic observations that we have, let's just use them. And 1 over n is less than y, as desired. That's it. So out loud, I did some rigorous justification that I think you can omit because how addition, multiplication, and inequality work for real numbers is something that I think we cannot need to write down explicitly. But the supremum property, feeling like something that's new, it's something that we're introducing in our study of real analysis, do cite that when you use it. Similarly, do cite the Archimedean principle whenever you use it, even if it feels like an obvious statement. Let's just treat maybe how the basics of addition, multiplication, and inequality work as the only things that we really don't cite in this course. And then everything else that we're building up, we will try to cite as much as possible because that's what makes your work rigorous. Okay, so I think that we're done. Let me just read through this. If y is a positive real number, 1 over y exists. Maybe if I were just writing this for myself, I probably wouldn't even write that. But by the Archimedean Principle version 1 that we've already proved, so it's fair to cite it, there exists a natural number which is larger than this positive real number. And therefore, doing some arithmetic with the inequality, all of which is valid from the order axioms, we get to what we want, which is that the reciprocal 1 over n is less than our choice y. Okay, that wraps up this look at the Archimedean principle. Thank you for your attention.